Hello, everyone. In the beginning, I'd like to thank the organizers for the kind invitation and the possibility to show the presentation, the results of my research. And as you can see, the title of my presentation is Integrating Functional Polymeric Adsorbents with Ambient Mass Spectrometry for Rapid Environmental Contaminant Detection. So basically, when we talk about environmental contaminants, we of course can talk about the inorganic contaminants and organic contaminants. And in my presentation, I'm going to be focusing on organic contaminants. So as we know, we can have various types of organic pollutants, and depending on the type of industry that produces it, that generates it, we can have a variety of compounds. For instance, agrochemical industry produces herbicides, pesticides, fungicides, fertilizers. The incomplete combustion of various organic materials causes emission of polycyclic aromatic hydrocarbons. The electronic industry basically produces polychlorinated biphenyls. Different spills produce, of course, generate the petroleum, different pollutants. And we can have emission of explosives due to a variety of activities such as mining, cladding, and different other activities such as, for instance, fireworks. On these compounds, I'll also be focusing. That's why I'm mentioning them. And basically, as you all know, functional polymers have various applications: tissue engineering, drug delivery, energy applications. But today, I'm going to be mostly talking about water treatment and how we can generate functional materials for targeted water treatment, water purification, and also combined with quantification. So basically, when we talk about the functional polymers for water purification or quantification, we usually want to use them for selective adsorption. So basically, selective adsorption works like this in the simplest possible system: that we have a sorbent, we have a solution that have various ingredients, various organic ingredients in my case, and it allows that the eluent is passed through the column, and of course the selective adsorbent only adsorbs the particular compounds that it was targeted to. So then we have the adsorbent. We can elute using a special elution system, for instance, strong acid, strong base, that breaks the interactions between the adsorbent and adsorbate to elute particular compounds that we are interested in. We can, of course, do this with different adsorbates. And then we get actually two things. First of all, we get the nice pure eluent with this particular compound that we are interested in. And secondly, we usually are allowed to get to lower volume than the initial one. So we get the pre-concentration factor, and it's quite important for the quantification. And of course, we don't have to do it in a column system like students do in classes and so on. We can do it on online system, for instance, connect the adsorbent column with HPLC system, so we can have an analytical column and adsorbent column, and do it online. So automated sampling, automated detection, and we can just relax and watch the whole system work. And what we have to remember is that the adsorbents can have a different shape or different structure. We can have the porous structures, like here. We can have microparticles or nanoparticle system. We can have random pieces of polymer, random chunks of polymer, or we can have just functional surface. So it's like a surface adsorption. And the polymers I work with I will be mentioning two types. First of them are MIPS, so molecular imprinted polymers. And molecular imprinted polymers are, let's call it, obtained in a special way. So basically, we have a template, an imprint here named, and to obtain MIPS, we mix it with functional monomers that produce usually non-covalent interactions. We can have covalent types, but most papers or most work are focused on non-covalent interactions. And then we allow the interactions to form between the template and the functional monomers, and then we add the crosslinker, and we start the polymerization. So basically, the polymer grows around the template to form a nice molecular cavity. And actually, the molecular cavity is formed after we wash away the template. So we can remove it, we break the non-covalent interactions by using, again, some strong acid, strong base, maybe some other system. It depends, of course, on what we have in the mixture. And then we obtain a molecular cavity. And the molecular cavity works in a way that whenever, again, the compound, in this case, it's usually the same compound. So in the synthesis is template, in the analysis analyte, whenever the analyte is present in the system, it becomes selectively adsorbed again in the molecular cavity. And of course, we have some kind of equilibrium here. And what are the MIP benefits? They have high recognition specificity because of the molecular cavities. We can predict the structure and we can apply them in different areas. They are quite robust. They can survive temperature changes and also various pH conditions. They can be quite easily prepared and usually from quite or relatively cheap ingredients. They of course have some drawbacks. We have some issues sometimes with adsorption size heterogeneity because it's a statistical polymer. So not all the molecular cavities have the same shape, the same strength of interaction. So there are some differences regarding they're homogeneous, but basically they are more heterogeneous. We have this effect known as template bleeding. So basically when we remove the template, usually not all of the template gets removed. And when we start the analysis in the continuous form, like in HPLC and so on, sometimes we see the template again in the eluent. So it's called template bleeding. Is of course a negative effect, and we want to be sure that all the templates is removed, which is not always that easy. For some templates, it's quite hard to make MIPS with high affinity due to their structure. And what is important, MIPS are mostly limited to acrylates, metacrylates, and vinyl monomers. Most papers, more research is done on this kind of polymers, and actually they have limited compatibility with water solutions. So it's important to remember that we still want to make MIPS with higher applicability for water solutions. And the second type of polymers I work with are HIPE polymers, so high internal phase emulsion polymerization. Basically, it works like this, that we have an organic phase in which we have the monomers dissolved. We add the aqueous phase in quite high amount, over 74 volume percentage. And the organic phase makes a continuous phase between the droplets. And then we start the polymerization. The polymerization only occurs in the organic phase. So basically, we get a nice pore structure, and the solvents, both solvents, actually the aqueous phase and the organic phase gets removed. So basically we get a polyHIPE structure. We can do this in the reverse combination of solvents. So it's the same way, just the other combination. And what I'm working with is ambient MS, so ambient mass spectrometry. It works like this, that we perform ionization under ambient conditions, so the atmospheric conditions. And there are various systems that works in this way. Basically, what we work with is the plasma system. So we have a low temperature plasma that's interacting with a surface or with the analytes. It ionizes them and takes them to mass spectrometer. Actually, our system is mostly the one which you can see below. So we have a heated crucible or heated place that we put the sample in. We heat it. We allow the thermal desorption of the analytes to occur. And then they enter the plasma stream, which ionizes them and also takes them directly for the mass spectrometer for the detection and quantification. And actually, our work, or my work with it, started when I was still doing my PhD. So we did the work when we used the magnetic scavenger. It was actually a commercial one, so it was a hybrid system. So it had the magnetic core, and we use it to adsorb different analytes from solutions. It were simple organic compounds like caffeic acid, benzoic acid, and so on. So we added the scavenger, collected with the magnet, and put it to the FAPA ionization system. So here we had the magnet with already our adsorbent collected, and the adsorbent already adsorbed the compound from the solution. And we did the FAPA analysis, so use the FAPA system to ionize the compound and analyze them in mass spectrometer. So here are the extracted ion chromatograms that we obtained. And actually we're allowed to nicely improve the limit of detection. The dashed line here is the threshold by using preconcentration on this system. Actually, this first work inspired me to follow that route, that science, and I was thinking about which materials can we use to even make the adsorption better or to higher degree. And that was the time when I started working with molecular imprinted polymers, MIPS. And initially I produced the simple MIPS, let's call it, so the one using metacrylic acid and EGDMA, ethylene glycol dimethacrylate, simple polymerization using ABN. the radical polymerization. And always when we do MIPS or other adsorbent, we investigate the adsorption isotherms. They're gonna be shown on later on my slides. That's why I always, let's say, tell a few words about what it is. So basically, we usually obtain the adsorption isotherms from imprinted materials, and for the non-imprinted materials, so like our background or our check, to check what is the difference between the adsorption of non-imprinted polymer, so the one obtained without the template, and the one obtained with the template. And as you can see, there is always a nice difference between the non-imprinted polymer and the imprinted polymer. The higher the difference, the better the adsorption capabilities of the imprinted material. And we use that system to quantify nicotine, propylphenazone, and methylparaben using our system. So here are the data for our system and also the limits of detection, and also linearity ranges, and compare them with other techniques. And actually we obtain better results than, for instance, voltammetry, also chromatography systems. So we actually show that this system works nicely with nicotine, propylphenazole, methylparaben for various simple organic compounds. And during that time, after my PhD, because that was the work which I still done during my PhD, I went for a postdoc to Professor Richard Hohenboom's group, who is a specialist in polyoxazoline chemistry. And polyoxazolines are very nice polymers that can be easily modified. Nevertheless, trying to obtain MIPS with them using, let's call it the same chemistry that we do with metacrylates is a bit challenging in the beginning, because MIPS are obtained, polyoxazolines are obtained using crop cationic ring opening polymerization. And this polymerization becomes terminated whenever a nucleophile is present in the mixture. So actually using the same system, so taking polyoxazoline monomers, adding template and trying to polymerize it wouldn't work, because basically most of the templates have some hydroxyl, amino, carboxyl group that would terminate the polymerization. So to solve that issue, we went for the short chain polyoxazolines, who is DP50, so 50 monomers in one chain, and use this short chain polymers as the initial polymers, and we cross-link them using diethylene triamine. So this is the schematic structure of the obtained MIP, and we use the indomethacin as the template. The initial work was we are supposed to make some polymers that will have prolonged drug delivery. So we investigated the drug delivery at various pH values, and actually what we have seen that there is some difference, but it's not tremendous. It's not, let's say, some big difference. So actually the results were so-so. Nevertheless, we investigated the adsorption capacities of the materials, and we have seen the huge difference between adsorption of NIPS, the non-imprinted polymers, non-imprinted polyoxazolines, and the MIPS, the imprinted one. And actually the difference was huge. It was almost 12 times higher, the adsorption capacity of MIP compared to non-imprinted polymer using the Langmuir model. So it was almost 12 times higher. Usually for metacrylates, acrylate system it's between 3 to 6, usually. So 12 times higher is a huge difference. And actually we wanted to go further with that system and use it for adsorption. So it's actually the one which I started to talk with initially. And we obtained we use the same system, C3-mestox, this time functionalized with 4-IMP, 4-aminopyridine, and we introduced the functionalities into the side chain. We used different amounts, so 0, no functionalization, 2, 5, 15, and 20% amount. And the template was 2,4,5-T, one of the chlorophenoxypesticides. So basically we investigated the adsorption capabilities of the system. And we also investigated versus the compound with similar structure from the same group, MCPA, so also one of the chlorophenoxypesticides. And we found out that actually increasing the AMP content for aminopyridine allows us to reach very nice selectivity factor, much higher than the one obtained for the materials with lower AMP content, and of course much higher than the non-imprinted materials. Also, we have shown that the selectivity factor nicely correlates with the results of the K parameter from the Langmuir model. The K parameter show more or less what is the strength of interaction between the molecular cavity and the template itself. So that's why we showed the nice correlation between these two values. And we, of course, made the FAPA quantification, ambient MS quantification, and showed the nice recovery values within the 6% of the true value using the river water sample spiked with 245T. Actually, the results were quite nice. We are allowed to publish it to Chemistry of Materials, and we were even asked to prepare a cover. So that was the idea. The professional graphicians advised us to make this nice diver with the net was supposed to be our MIPS, and the hazardous jellyfishes were supposed to be the one glowing. So it was the system was only collecting the glowing one, leaving the one without the glowing effect untouched in the water. And we liked the idea, but unfortunately the editors didn't like it and the cover was not chosen. I mean, our picture was not chosen for the cover, but still I have a nice image that I can share with. Nevertheless, we follow the same system, also C3 Maxtox crosslink with data, this time to imprint it with 3 different explosives, picric acid, FDX, and P10. So actually the explosive from 3 different types of the explosives, let's call it. And actually we're allowed to work this because we had an industrial PhD. It was a firefighter, but he was from the unit which actually is called whenever there's a chemical danger, and he mostly specializes with the hazards connected with the explosive materials. So basically he worked on his PhD with explosives, and we did that work together. So what we did, we obtained the MIPS imprinted with picric acid, RDX-P10, like I said, and here is the scheme of the work. So we investigated the binding, we investigated the quantification with FAPA, and here is the exemplary, here are the exemplary adsorption isotherms from NIPS and MIPS. These are actually the one obtained for picric acid, because as you can see, the differences in adsorption capacity between the NIPS and MIPS are the highest one for picric acid, which was expected by us because, of course, picric acid is an acid, so it has a high affinity for materials with basic character, and the MIPS obtained are mostly basic due to the amine groups. Nevertheless, we obtained nice difference also for FDX and P10, but not that high as in the case of picric acid. We, of course, investigated the quantification in river water and wastewater, 2 different systems. We obtained nice limits of detection, especially for the picric acid 0.01 micromolar. This is very nice limit of detection. And we also got very nice recovery results, also within, as I recall, 8.1% from the true value, which is also quite nice result. We, of course, not only work with poly-C3 Maxtox, we use different types of polyoxazoline for the functionalization. We use polybutanox, so this time we have a double bond in the side chain. And in this research, we functionalized it with 3-mercaptopropionic acid to introduce the carboxylic functionalities. Again, we functionalized with zero, no functionalization, 10, 20, and 30% of MPA content. And the other double bonds were, of course, used for the cross-linking in the presence of MCPA, again, one of the chlorofanganoxy pesticides, to produce nice MIPS with cavities of exemplary structure presented here. We, of course, investigated the adsorption isotherm. As you can see, the difference are not that high. The best one are obtained from the MPA with the highest MPA content. And the limits of detection are almost the same actually for 3 initial MIPS, so 0, 10, and 20% of functionalization. For the one with 30, we actually got a better limit of detection, well, twice better compared to the other 3 ones. For the NIPS, the results were all the same. So actually the functionalization allowed to slightly improve the limit of detection. We use similar system. So again, polybutanox, this time functionalized with 3 different compounds. Again, MPA, so the same functionalization. Also phenyl with methoxy group, and also introducing hydroxyl group. This time for quantification of propylparaben. So one of the preservatives which are used, for instance, in cosmetics. And again, the scheme of research, the adsorption and quantification. And this time, actually, we obtained differences, let's say not huge ones, because maybe I'll show the limits of detection initially. So actually all the limits of detection are the same for MIPS. So we can see some differences regarding the absorption capacities. Nevertheless, they are not big enough to influence the limit of detection for MIPS, which actually we got the same for all 4 materials. Nevertheless, what was a nice improvement was the selectivity factor. We used a mixture of propylparaben, butylparaben, and benzylparaben. All 3 parabens can be used as preservatives in cosmetics. And actually, functionalization with the MPA, the carboxyl group, got the best results from selectivity factor. Nevertheless, all 3 functionalization improved the selectivity factor over the non-functionalized MIP. The differences, like I said, there are some noticeable. Nevertheless, they are not like a game-changing. We also functionalize PE-based materials, so we take the polyethylene amine, functionalize it using the epoxy group, so actually no byproduct, which is important for MIPS chemistry, and we cross-linked it. We introduced the functionality as a 2-hydroxyl group, functionalization with glycidol, and we cross-link the system using 2 cross-linkers, BDE and NGD, that's the abbreviations. And again, 2,4-D is one of the chlorophenoxy pesticides. And here is a lot of results, sorry for that, but basically, as you can see, the differences in adsorption isotherm are not that high. Actually, the best adsorption capacity was obtained for the unmodified material, so this one, so a bit different than the one which I showed you previously. And the limits of detection for all MIPS are the same, except the one with the highest glycidol contact and also crosslink with NGDE. This is this one. We actually got slightly worse limit of detection than for the other ones, so that was not improved. Nevertheless, we obtained better selectivity factor for the functionalized, the one with the glycidol, so actually the selectivity increased, but the overall capacity has gone lower. It sometimes happens. Yeah, but still the selectivity for all MIPS is much higher than the one obtained for non-imprinted materials. We also did functionalization using 3 different systems. So this kind of ionic system, abbreviated here GTMAC, introducing the furan group and BGE, so just alkyl chain. Again, using the epoxy compounds and cross-linking using the only one, this type of cross-linker in the presence of 2,4,5-T, again, one of our chlorophenoxy pesticides, one of our most, the group which we studied the most. And this time we obtained a much bigger difference. As you can see, interestingly, the BGE actually got the highest absorption capacity, so the one with just the alkyl channel. We think it's connected with the hydrophobicity of the material. The lower one was obtained for GTMAC, the green line, and actually introducing the furan group almost didn't change the absorption capacity of the material at all. The limit of detection well nicely improved only for the BGE, so actually this absorption capacity allowed to improve the limit of detection. The other ones are still the same. And also the BGE functionalization improved the selectivity for a noticeable extent over the other 2 functionalization types. We also work with other polymeric system to work with MIPS, not only the polyoxazolines one. In this case, we work with polymethyl ethyl alt maleic anhydride. This polymer functionalizes with 4-AMP. This is a nice system to introduce the pairing units and obtain this kind of polymers that we can then nicely cross-linked using the amines. And here is the exemplary molecular cavity with the 2,4-dichlorophenol. That was our template. So here are the absorption isotherm. Introducing the 4-AMP actually nicely improved the absorption capacity. And also we got improved in limits of detection, again for the material with the highest absorption capacity, so with the highest amount of 4-AMP functionalization. Also, we work with porous materials, so that was the part connected with molecular imprinted polymers. Here are the porous materials. So in this case, we use the HIPE procedure. So we take the two-solvent system. This time the polymerization the cross-linking actually is conducted with the presence of catalyst TBD. And we use it for adsorption of 2-chlor-difluorophenol, bisphenol S, and 2-naphthol. To get a nice porous structure, here is this, just the scheme. Here is the same structure, the same picture. And we nicely improved the limits of detection. The HIPE 4 were different composition. The 04 had the highest porosity. So actually that was not, it was not very surprising that the material with the highest porosity actually allowed us to reach the best limits of detection. And also we use the system again with explosives. So the same system with explosives with picric acid RDX-P10, the one which is studied before, as you remember. And again, the best limits of detection were obtained for picric acid for the materials with highest 4 AMP contact. This time we use the same system, I mean the composition, regarding the solvents and so on, because in this case we changed the solvent system and so on. And in this case it was the same, just the differences were in 4 AMP content, so the functionalization degree. And for the two containing 10 and 20% 4 AMP, we got let's say quite similar adsorption capacities, and also we got the best limits of detection, especially for picric acid. Our future plans involve broadening, let's say, our spectrum of analytes to POS, the perfluorinated compounds that we actually are already finalizing the manuscript. Because POS they were banned by European Union this year. They are supposed to be withdrawn from cosmetics and many other products. There is a resolution about this. So they are quite hazardous because they are accumulate in the living organisms, and also they do not degrade almost at all. They are known as the eternal chemicals, or they are so called. That's why targeting them to have a nice procedure to quantify them rapidly in the environment would be demanded. And also we want to go in a completely different area. We want to make a photocatalysis, so have a carbon sponge covered with titania, and also with MIPS. The MIPS will be supposed to improve the adsorption capacity of the material and also target one particular contaminant. And the titania will be responsible for the photodegradation of the compound. So this kind of hybrid system for targeted adsorption and targeted degradation. And conclusions, there's a lot of conclusion, but to be more, let's say, rapid, or just to mention them, the functionalization of polymeric adsorbents, especially MIPS, offers high selectivity, stability, and reusability of the materials for the adsorption of organic contaminants. Polyoxazole MIPS and PAVE-based MIPS can easily be functionalized to recognize particular contaminants, especially for environmental applications. Connection of solid phase extraction with ambient mass spectrometry allows for rapid solvent minimize and direct quantification on various contaminants. And also this attempt or this system, we think in the future can be field deployable. So actually to make the system more that it can be taken to the environment to make a quantification on spot or in particular price. Polyhipes allow to obtain materials with high surface area that actually improve the adsorption capacity of the materials. And in future, we want to focus more on phos-specific MIPS and probably also porous material to make a nice platform for these contaminants which are now removed from the market. I want to, of course, thank all the members of my group, the postdoc, PhD students, master students. Also, I want to mention the collaboration that we have with Professor Richard Huchenbuhr regarding the polyoxazolines. With Verona Jordache, we now have shared project. With Wiktor Jerka, we share information about the polymers, and also we want to start some shared work with PIPOX. And there are local collaboration in Poland with Center of Advanced Technologies. And of course, I want to and I have to mention the support of our local financing agencies. In the end, I want to invite if you ever visit Poznań, Poland, you can visit Poznań. Poznań is located here, more or less between Warsaw, our capital, and Berlin, which my laser dots start working bad, but no, Berlin is not where the laser portion is now. It should be okay, somewhere here. This is our old market square, known for these colorful small buildings. We are famous for the sweet croissants. So this is the picture to make you interested in them. And when you visit them, visit Poznań, you have to try them. It's only our regional dish. And here is my chemistry building when I'm sitting right now, more or less in this spot. And here is the monument of the guys who broke the Enigma code. They are from my home city, the guys who initially broke it. So we have a nice museum of that. And in the end, I want to, of course, thank you for your attention.